A very warm welcome, everyone, to this seminar series. Today, we have Jeremy Butterfield and Faye Dowker, who will talk about recovering general relativity from a Planck scale discrete theory of quantum gravity. Thank you very much for accepting the invitation, Jeremy, and I leave it all to you.
Well, thank you, Sylvia, for the invitation, and thank you, everyone, for coming. Yes, so needless to say, this is really Faye is the lead, but she and the community that she works in called Causal Sets, as many of you will know, she's in this Causal Set program that was spearheaded by Raphael Sorkin 30 years ago. They have an absolute custom that you use alphabetic ordering of names. So it's most unfortunate, but I could never convince Faye. That's why you see my name. So here we go. Right. The topic then, in the general philosophy sense, is there are discrete and continuous structures, and in particular models of space or space-time. And one naturally asks, well, what does it mean for the discrete structure to recover a continuous one? Or to put it the other way around, this is just introducing the preferred Faye and Jeremy terminology. What does it mean for a continuous structure to approximate a discrete one? And all of us, when we hear that word, having studied a little bit of physics and philosophy, will say, well, what it must mean is that the discreteness is on such a small scale that it looks continuous. And that will mean that that tiny scale where the discreteness kicks in is something about which the continuum lacks information. Of course, the continuum C, the continuous structure, may have lots of other information, but it doesn't encode the tiny scale at which the discreteness of D is occurring. Now, I know it's a mixed group of physics and philosophy, and so I tried a little bit to use both jargons. Recover and approximate would be nice heuristic words in any physics or philosophy discussion, but there is a philosophy jargon which is a bit more special. It's called supervenience, but the physics jargon for it is saying determined, meaning completely fixed by. So the idea would be D is the really informative microscopic details, but if you lose some information, you can obtain C. So it is, as we would say, and we used to say this even before Zoom came into our lives with the pandemic, you zoom out from the micro details and you only see the smooth. So C contains less information, or as in physics jargon, you might say C is a coarse graining of D. So that's the rough idea that I think everybody would agree about. And the more flexible or precise way of saying it is something like C is essentially determined in the sense that although given a D, capital D, discrete, it might be coarse-grained in two ways, C1 and C2. You don't allow arbitrary coarse graining to throw away lots and lots of information so that C1 and C2 say almost nothing. No, it must be true that in order to approximate D, two items C1 and C2 that both approximate D have to have differences that are small. So C is a logical weakening or a coarse graining of D. It is supervening on D, but it doesn't throw away so much information. In fact, the idea will be that C1 and C2, if they're both good approximations, they have differences that are pretty tiny. I mean, they're the sorts of difference you see at the scale at which big D is relevant, right? They have differences that don't really count to the way they approximate D. So in the jargon of maths or physics, bottom of the slide, if we now say, no, let's get specific, we're talking about space, and so D and C are metrical or geometrical spaces or structures, the idea would be that there's some kind of approximate isometry between any two C, which are good approximations to the D. Okay, so that's the general idea. So what are we going to do? Well, this paper is a sort of, well, I think it's fair to say it's an advert for causal sets, because it says causal sets do something that you want done. And in a certain sense, there seems nothing else that does. So we're going to make two assumptions, and then we're going to make two claims. And the first assumption, well, both assumptions are about any theory of quantum gravity, which we call X. And we're going to assume that X is to recover general relativity. And we're also going to assume that at the Planck scale, X is discrete. And we're going to introduce some jargon with which to give more detail about these assumptions. A grounding state, which won't have anything to do with grounding in modern philosophy, but it's things like the micro state with all the detail on which other stuff will supervene. So it's at the bottom, so to speak, in the usual metaphor of levels. And the discrete physical data and the discrete continuum correspondence we will see in a minute, but discrete continuum correspondence is going to be all about the slide I just gave you, all about that recovery and approximation. And so with the assumptions as we make them more precise, then there are two claims. One is that causal sets, which are a certain kind of discrete order, thought of not for space, but for space-time, they recover general relativistic spacetimes. And on the other hand, this is a sort of challenge to the literature. So far as we know, in particular, so far as Faye knows, there's to date no other proposal for a DPD set that recovers. And so that's the plan. And the result is that in these slides of mine, I'm just going to talk about so there are two assumptions and two claims in the light of what I was saying earlier. I'm going to comment about the assumptions. There are various analogies to what we've been discussing about recovery and approximation. One is that relativity recovers Newtonian gravity as an approximation. Another, which is closer to what we're concerned with, is that molecular dynamics recovers fluid dynamics as an approximation. So the continuum model is emergent in such a case. And that quantum mechanics recovers classical mechanics as an approximation. And that is contentious, of course, because of the quantum measurement problem. But different authors will take different views. Some will regard that recovery as already established, or they will regard it as something that is yet to be established. But everybody agrees that it must be the goal. And our assumption number one then is that this quantum gravity theory X, whatever it is, must recover some large class of four-dimensional GR spacetimes of the type that we know to be so scientifically successful in detailed prediction and modeling. So one needs to recover treatments of gravitational waves or Minkowski space, not as a model of the cosmos, but there must be large portions of Minkowski space that get recovered by X. and there should also be black holes and expanding cosmologies, and all these recovered spacetimes are going to be not having a lot of variation in their quantities on very small scales of length and time. So we envisage, here's our jargon, that X has, for any space-time manifold, comma, G for metric that is going to be recovered, it has a grounding state, which in some way it contains, or it produces, or it implies, or it gives rise to discrete physical data, from which indeed mg is going to be recovered essentially uniquely. And this goes back to my first slide with kind of two continuous structures, C1 and C2, need to be approximately isometric in order to count as good approximations to the discrete structure below. So, whoops, sorry. So the DPD doesn't contain geometrical information about the GR spacetime at smaller than Planckian scales. And to spell this out a tiny bit more with our jargon, then for any theory X, there's going to be this discrete continuum correspondence that says that up to some tolerance, when a GR spacetime is recovered from a DPD set, and the natural analog is the molecular state determines the fluid state, there's a correspondence there between the discrete micro and the continuum approximation. So the idea of the essential uniqueness is then spelled out in this comment number 6. It echoes the philosophy jargon of supervenience, or the more general jargon of determination. Sorry, it should say mg and mg prime, right? If mg and m prime g prime are both recovered by the same DPD set according to DCCX, then they must be approximately isometric and physically indistinguishable on large scales. And that is making more precise the idea that one theory recovers another. Okay. But we're not making any assumption about the grounding state. It could be a state in Hilbert space, or it could be something entirely different. And we make no assumption about how the state gives rise to the DPD. That doesn't matter. The DPD could be expectation values of certain operators, or they could be eigenvalues of those operators. And the deduction from the state might involve some coarse graining from the grounding to the DPD. It could involve anthropocentric arguments about what observers are liable or most likely to observe, so that there is a what is called an observation selection effect in obtaining the DPD, and so on, right? And finally, the argument is not going to target two research programs or overarching themes in research programs in quantum gravity, which are not in the relevant sense discrete. Namely, some people work with Lorentzian manifolds, so it's a 4-dimensional manifold M with a Lorentzian metric little g added to it, but the Lorentzian manifold consists of flat patches like a polyhedron, and these flat patches meet at edges, and the corners at those edges could be rounded, if you wish, so as to make it a very honest and rigorously a Lorentzian manifold, or they could be crisp edges where things are not smooth, they are not rounded, and then what people talk about a stratified manifold. But that's a small matter, that difference of rounded or sharp on the edges. What does matter is that there is continuum information in the middle, in the interior of the flat patches. And nothing we say in defense of causal sets will be against this flat patch polyhedron built from flat patches vision, right? The other thing that is not a target is when you talk about a discreteness length, but then you in fact take it to zero in order to define your theory in the continuum limit. And in the paper, the example mentioned is the elementary definition of a path integral. You draw zigzags up the page of the continuous but non-differentiable path in space that a point particle might undertake, and this contributes to the total amplitude for the transition concerned, and the length of the zig or the length of the zag, call it L, is then taken to zero, and the path integral is defined in that limit. And of course, it is hairy because the mathematical structure at the limit is different from what it is on the way to the limit. I mean, you're in an infinite dimensional path space, and but that isn't, in our sense, discreteness, because the regulator L, the length of the zig and the zag, has been taken to zero. Okay, so that's the end of my slides, right? Okay. So now, in our jargon, I hope you can still see it and hear me. Claim one, this is the positive. Causal sets are good. They represent a set of DPD, which, if you think of them as being discrete on the Planck scale, they do well. And with the limitations, especially of the last comment I made, which sets aside piecewise flat Lorentzian manifolds and sets aside defining a theory at the limit, claim two, causal sets are the only thing known to work. So here is a slide just emphasizing that Lorentzian geometry is very different from Riemannian geometry. The dots on the hyperbola are all equidistant from the point P. They're all one second of proper time to the future of P. Some of them look far away from.
Sorry, we're still in the previous slide. I think you're not sharing the.
Oh, thank you, Alvaro. Okay, right. Can you now see a light cone?
Yeah, that's perfect.
Okay, so in this picture, we emphasize that Lorentzian geometry is very different from Riemannian geometry. The dots are all equidistant from the space-time point P. The points can all be imagined to be 1 second of proper time to the future of P. Those that look so far away are really, it must be said, physically just as close to P as those that look so close. This is relativistic time dilation, but that is, in a certain sense, an appearance. The objective Minkowski distance between each of the points and P is the same. So, as Fay wrote, Lorentzian geometry is bordering on non-local, really. And pictures that we draw don't capture well what's going on. This will be vividly important in the example we'll come to at the end. So causal sets are discrete sets with a binary relation, which you could think of as precedes. You're to think of A, B, C, and D as point events, D lying to the past of both C and A and C as being space-like, A to the past of B. And so this sort of, in such a diagram, you do not draw the arcs or edges which logically follow from those you have already drawn. So the logic word is transitive, which means that if alpha is related to beta and beta is related to gamma, then alpha is also related to gamma. So D precedes B in these diagrams, but we don't draw that because we only draw the minimum sufficient collection of arcs to determine the complete collection of relations. And if you read the causal set literature, you find these stupendous numbers about how densely, by our macro standards, the causal set nodes are distributed in a space-time that they are said to recover, right? The 10 to the 240. But the background idea is that causal structure is almost all of geometric structure. And this is a bit more technical slide that fills out the idea that Lorentzian geometry is almost all causal structure. The word number at the top is expressing the idea that you are to have one such point of the causal set in each tiny Planck volume of space-time. So the official doctrine in our jargon for how causal sets are going to recover GR spacetimes is that the causal set must be injected one-to-one into the mathematical spacetime M, G at a Planck density, which means that, as I just said, per Planck volume, there is about one. And the causal order, the pattern of arrows that we had before, of the given causal set exactly matches what Lorentzian geometry says about the embedded points in M, G. So the causal set community has been going for some 35 years. I think it was 1987 that Sorkin, Bomberly, and I think Myers wrote Space-Time as a Causal Set as a physical review letter. And a great deal of work has been done since by, in particular, Sorkin and Fay herself, and people like Meyer, Meerheim, Brightwell, Rideout. And the second rectangle here reports that quite a lot of work goes on probabilistically distributing points in manifolds and examining the statistics of that sort of distribution. The Poisson distribution is the central stochastic idea used in that kind of work, right? And so that's sort of encapsulated in the rectangle. Anyway, as some of you will know, there is a theorem in general relativity which catches the idea that Lorentzian geometry is almost completely defined by causal relations. It is a theorem that puts together some 1960s work, a 1967 paper by Cronheimer and Penrose called, I think, Causal Spaces, an early 70s theorem of Hawking, and then a finishing theorem of Malamud in the Journal of Mathematical Physics. the idea is a Lorentzian metric is fully defined by causal notions together with a counting measure, or sorry, a conformal factor, a single further number to complete the 10 degrees of freedom at every spatial point in a four-dimensional space-times metric. And the summary of what the big rectangle says more formally, the causal order of the causal set provides the space-time causal order, and a counting measure, little Roman 1 above, provides the volume. Many of you will know that Riemann in 1854, in his amazing inaugural lecture, talks about discrete manifolds and talks about counting as providing the notion of measure in a discrete manifold. So various bits of evidence for this program modeling general relativity well. For example, capturing in causal set language notions of dimension, catching in causal set language notions of scalar curvature. So one can find, so to speak, ingredients at the bottom level of causal sets which model or recover or get approximated by the continuum notions. Okay, so here is claim 2, that nothing else does. Here is a proposal for an alternative DPD. So I'm moving now not to celebrating that causal sets do well, but to the negative argument that something you might hope does well to recover space-time has trouble. So I'll call it a combinatorial Lorentzian Red-J complex, or in fact, I'll call it a CLRC for short. And as you will know, simplexes like a single edge or a triangle or a tetrahedron can be put together as one, as I said earlier with the word polyhedron, put together in what is called a simplicial complex. And if I say my triangles and edges and tetrahedra have got no length information, that would be very, very non-metrical. It would be very, very just combinatorial. It would be what a graph theorist would call a graph, where no notion of metric occurs. But I want to allow edge lengths to be given to the edges. And if they are future directed or past directed, let that also label the edges. And I wish to postulate in such a CLRC that no more than a few Planck units between any two vertices. It's called combinatorial because I am very specifically not allowing I'm not postulating some flat Lorentzian metric in the interior of the triangles. So that is the warning beside the picture. I declare that the picture is not to be taken as having flat panes of glass with a flat continuum geometry between the metal struts. It just has the metal struts, each with a Lorentzian metric, okay? Sorry, each with a Lorentzian length attached to that edge. So here is a natural suggestion for how such a mathematical object could recover continuous spacetimes. We'll say that the spacetime, starting from the spacetime M, you could choose a set of points in it and connect them up by lines, in particular, say geodesics, and thus triangulate, as people say, the manifold M. And that is indeed a combinatorial complex. That is to say, it's what a graph theorist might call a graph. And that would be condition one of what it is for a particular CLRC to recover a GR spacetime. The second component, little Roman 2, is that the vertices can be embedded in the manifold in such a way, of course, that the space-time geodesics between the embedded vertices have lengths equal to what the edge lengths were in the CLRC. So this is just spelling out what you almost certainly had in mind during the previous slide. Okay, so it's a promising way to think of the continuum of space-time being recovered from a CLRC. It's very like the way causal sets were to recover a GR space-time. There's an injection which preserves the assigned relations. In the causal set case, it's causal order in the causal set gets injected into causal order in a GR spacetime. Here it's Lorentzian geometry edge lengths that get injected. Okay, so here's the reason this doesn't work. There's going to be a CLRC which does indeed recover Minkowski spacetime, but it fails the essential uniqueness requirement. It also recovers a spacetime that is a perturbation of Minkowski space, namely a perturbation which has got a gravitational wave burst crossing it. And this is the punchline. Here is 3 + 1 dimensions, but I've suppressed 2 dimensions. There's a spatial direction Z, a temporal direction T, and therefore, discretizing, I can write down the integer lattice in this 4-dimensional space. And if I fix x equals y equals 0, or x equals 5 and y equals 2 or something, and look at the plane of z and t, I get the display of black dots. And the blue region, of course, represents what you might call a pathway for light or very fast matter to move from the left to the right. Evidently, lower times are to the left and higher times are to the right. So each little square, in fact, it's a hypercube, and you can then begin to count the number of simplexes in these hypercubes, and the CLRC, the official CLRC, is to be the combinatorial complex with the edges decorated with their Lorentzian lengths and their future direction. That is to say, for the time-like and the null ones, their future direction. But notice that there is in the shaded region, there are no vertices. It is a void, okay? And furthermore, goes back to that final comment on the restrictions of our assumptions. By discreteness, we really mean discreteness. We do not believe, we're not considering a theory in which flat patches of continuum geometry are part of the discrete theory of quantum gravity. Okay, so the CLRC discrete continuum correspondence does declare that this CLRC recovers Minkowski space. But the trouble is that I can put a wave, a gravitational wave, through this blue channel, and it will not register any difference in the CLRC. That is to say, here below is a metric. It represents a plane wave burst gravitational wave traveling in the Z direction. with mild conditions on H, and U is defined as T minus Z. So this function H is what is giving the perturbation in this region of the Minkowski metric. And the punchline, or the bit thing that's hard to get your mind around when you first meet it, is this void, though you look at it and you think, oh, Butterfield, but look, between the origin of the diagram and 1 unit up vertically in the square labeled big Roman 1, that's tiny. That's a single Planck time, some tiny thing. But that is an illusion of the diagram. Go back to the light cone I first began with the dots, where I emphasize they're all equidistant from the central point P where the light cones intersected. You could have drawn a happy little diamond between the evidently nearby point just above P, and you would have said, oh, there's a nice little causal diamond. Its total temporal length or lifetime is 1 second, we said. But if I had taken one of the points way up the light cone and drawn a corresponding diamond, it would have also had temporal length 1 second. Just boost yourself to a frame in which the straight line from P to that point is the world line of the observer to whom you are doing the boost, right? So this blue region contains lots and lots of approximately flat causal diamonds of height 1 second, right? And the CLRC doesn't register it because there are no vertices in this blue region, right? And of course, you do need very large gamma factors, like 10 to the 44, to find such a pleasant causal diamond in the blue region, despite the fact that it has been set up to look tiny, as in my opening comment about the square Roman 1. Okay. On the other hand, if we were doing Euclidean or Riemannian geometry, then this void is not a physically nice region of Euclidean spacetime. It's got physical structure that's smaller than the Planckian scale, and the wrinkle of a gravitational wave burst would not be in any way altered by an isometry. Okay, so you could conjecture that, but we haven't tried to do it, that if one wrote down combinatorial Riemannian Rete complexes, you could have some theorem that there is a systematic ability to recover Euclidean spacetimes. Okay. So in effect, summing up, whatever the DPD set is in theory X, if you don't have a number volume correspondence, there are likely to be large physically nice void or sparse regions. And when there are large physically nice voids, any DCC for your theory X is going to fail because the DPD set isn't going to recover the Lorentzian geometry in the voids. But if you want a number volume correspondence, then causal sets, so far as we know, are the only things that do it. And then there's some remarks about quantum uncertainty, which I don't want to go into, we're running out of time. No matter what X is, fundamentally, the argument goes, if we have our assumptions accepted, then at present, the only way to recover a GR spacetime is by a causal set. So thank you very much. Okay, I'm going to escape from the full screen mode.
Thank you very much, Jeremy.
Thank you.
I can see that already Carl raised his hand. So
yes, I really raised my hand while Jeremy was still talking, because it was a clarification question about the last argument with the void.
Right.
It seemed to me that a role was played there by the fact that these nodes that you drew onto the picture were spaced evenly rather than aleatory, or rather than randomly according to some random distribution. And if they were placed randomly, then you wouldn't have any more this problem that there exist big void spaces without any vertices in them. Is that right?
Yes, you're right. The CLRC program could be developed so as to rule out the counterexample. The nature of the counterexample is that a double success is a failure. It is the fact that the CLRC doesn't distinguish between Minkowski spacetime and this plane wave burst. So it's an open-ended situation, and it's very astute of you to see that there's an issue here, and where the CLRC person may hope that some kind of strong claim of typical CLRCs recover unique spacetimes can be maintained. So you're right. I think in that sense, it's a limited target. But that's a first step for the CLRC program. I mean, it's not obvious that it could be done. It could be that if you specified some aleatory process, and thus had a notion of typical or most likely, a similar kind of example could be launched. After all, let the points go where they may. Faye will design her example perhaps so as to exploit the voids that any such CLRC provides. But it is true that in the example as it stands, the CLRC is not the result of an aleatory transy process. Yeah, thank you, Carl. Good point. Yeah.
Are there other questions? Yes, Alvaro.
Yeah, I thank you for the talk. It was really nice. I read the paper, and when I read it, I think I understood why there was a difference between the Lorentzian and the Euclidean case, but now I'm not seeing it anymore. So maybe you can you go again and repeat why you cannot add some perturbation into the Euclidean case, so that there could be a difference in that case?
Well, I suppose the yes, it's not very clear in my mind actually. And when we were drafting the paper, we were going back and forth about whether to try to be very official about the Riemannian case, and decided it was best to say nothing because it wasn't for us to defend the Riemannian ability of the combinatorial complexes to manage. I hope that when I was talking the very opening slide about for discrete and continuum, what must be involved is that the continuum in some way lacks information on the tiny scales at which the discrete kicks in. Or if you like, it's got information, but it's the wrong information. I mean, it says everything is smooth and the discreteness kicks in. That was meant to remind everybody really of a newspaper picture, or nowadays digital photography, any picture, you know, pixels which the human eye cannot distinguish one from another, so that although the image is microscopically discrete, it is seen as analog. So that intuition, of course, is rooted in Riemannian geometry. Makes one think that if you are allowed to pick the discreteness scale as small as you like, you can surely approximate, you can surely recover, to use our language, you can surely recover the continuum, even if the continuum is very wrinkly. The idea would be, oh, let the continuum have rapid variation on small length scales. If I make my discrete structure even more fine-grained, the discreteness will be able to model the rapid variation. So if we think of micro and macro, and in between there is meso, my discussion, I confess to you, was always micro and macro. But it's quite natural to say something like, oh, imagine that the continuum does not vary only slowly on the Planck scale. Let it vary quite substantially. Well, in the sheer maths of it, an advocate of the discrete will say, well, I will then make my discreteness scale even smaller, and I will be able to recover the continuum, because on my even smaller discreteness scale, it will be varying slowly. And I believe that that pixel-like or digital photography intuition is underlying the Riemannian case working okay, right? So anyway, I hope that helps a bit, yeah.
Yeah, thank you. I have another question, but I don't know, maybe it's could be better for Faye. Like, I'm familiar with some quantum gravity models, like spin foams, and which they have similar structures, but they're not quite the same. Instead of defining like the lengths of the regulated triangulation, they define areas of triangles and tetrahedra.
Yes.
I was saying that there are these models in which instead of caring about lengths, they care about areas.
Yes.
So they have a similar structure, but they care about areas, not length. So I don't know if you have given a thought of how this kind of argument also applies to these structures.
Yes. Well, this is really a question for Faye, of course, but I think from our discussions, I mean, Faye is really, you know, not just a great expert, but also very craftsmanlike and careful. And in our discussions writing the paper, I think it's fair to report her as saying she believes it's a question for them, because there are so many different details in spin foam literature. But it is true that, like the slides and the written paper emphasize, many programs have sufficient continuum information in the bits or in the ingredients that we would not be claiming to refute them. Right. But it is true that there's a large, what you might call survey work to do, which is to know enough about, so to speak, 3 or 4 different programs that one can kind of catalog the amount and the detail of the continuum information they are appealing to. Yeah. But I tried to read some of these things, as one does, and there is so much intellectual technology, it is hard without having some long conversations with a real expert to know what are from this perspective the main features. But broadly, the areas and the volumes of spin foams or Regge calculus or causal dynamical triangulation, they largely avoid the gist of this argument, I think.
Yes, this was actually my question, but probably Faith here. So because I was thinking about GFT or other approaches indeed.
Yes,
and,
yes.
And it came to my mind that, let's say, I'm not entirely sure that this argument can apply to the GFT case.
Yes.
So
yes. I mean, I also asked Faye what she thought about GFT, but for me, my main person I happen to know is Daniele Oriti in this, and I have not had the chance to ask him. Yeah. So I'm afraid, I'm sorry. It's
we will have to repeat actually the meeting again with Faye some other day. Are there other questions or remarks? Or
I do. I have some.
Yeah.
Sorry, I interrupted you, Jeremy.
No, go ahead, please.
Just a couple of clarificatory things that I jotted down while you were talking. One is that near the beginning, when you were giving the concepts, you talked about the C model as a coarse graining of the D, which struck me as a very strange thing to say, because the C is the continuous and the D is the discrete. So
yes.
But I guess you just mean in a sense there's information lost, because
I meant there's information lost, but there's also what you might call misleading extra, which isn't real information. It's just smoothing, isn't it? So I mean, roughly speaking, I do apologize. Yes, I think coarse graining strongly suggests, even implies, less information without any extra content, even misleading content. So, and it's true that if you take, as it might be, 3 points as arguments of a function, and you have 3 values, and that's a very discrete structure. There are 3 arguments, and each of the arguments of this function delivers its value. And you then say, this is a real valued function, and now I'm going to draw a smooth curve through the 3 values. So clearly, everything apart from the 3 achieved values is misleading extra content, isn't it? So it doesn't really count as a coarse graining. It's a logical strengthening in that case. So yeah, I do apologize. Yeah.
It's not a question of apologizing. I just was puzzled by the. But I guess relatedly also, the framework you set up allows for two different continuous models to be grounded in a single DPD.
Yes.
Which makes sense. If you're starting from the continuous models and then saying, okay, what DPD would approximate this? It makes sense that you would have a many to one. On the other hand, if you were starting with DPDs and you were thinking, okay, what kind of continuous model is this grounding? Wouldn't you like to have a recipe that is unique, gives you a unique continuum?
Yes, I mean, so the spirit of the paper is very much the second option.
Mm-hmm.
And that's why, but on the other hand, well, you know, for you and me as philosophers, you know, we got the idea of kind of the ideal, very simple reduction of one theory to another, where you deduce the reduced theory's content absolutely exactly without error bars. That's, if you, never mind that if you kind of set aside the apparent difference between an individual structure and a theory, the idea might be something like there is a discrete structure and you can, in sheer logic, grind out a unique continuous approximation to it. It is true that the causal set program, or people in quantum gravity generally, or even, I suppose, people who do discrete geometry in a more general way, they're not concerned to always get absolutely unique as a cognitive ideal that, you know, you would attain if you could. No, the vision is, the continuum is yesteryear's theory or postulate, and it shouldn't be recovered wholly right. Therefore, what we need is a full microscopic detail, call it the discrete thing, and that is meant to give you a collection of close cousins, as all of them good approximations to this discrete real McCoy. So that's why there was that stuff about approximate isometry at the beginning. And well, in fact, the causal set literature has a wonderful German word called the main conjecture, Hauptvermutung or some such. I don't know German, I do apologize, which is the conjecture that under certain conditions, any two Lorentzian manifolds into which a causal set embeds will be approximately isometric. But that word is approximately isometric is itself a vague phrase, because it sounds highly technical when you first hear it. But of course, it does raise the question of what exactly do you mean by one metric, one, e.g. one Lorentzian manifold being almost the same as another. So one gets into this question of the space of Lorentzian manifolds and topology, or something even more subtle, such as a metric structure on it. And that's a hairy and ill-defined field. I mean, Frey's own, I don't think she'd mind me saying this, her own view, and the view of most folks in the causal set program, I think, is that it isn't worth now going all out to make this Hauptvermutung precise and prove it. It ought to come out later in some appropriate dynamics for how causal sets grow. And this is something that the whole presentation didn't touch on. The whole presentation was, so to speak, block universe. There's a whole causal set. It's going to be the discrete underpinning of a four-dimensional space-time throughout all history. And so the whole discussion today was kinematic. But anyway, I'm just mentioning that you're absolutely right. This many-to-oneness is a subtle matter, because you want uniqueness of, but only essential uniqueness. Uniqueness up to small differences is yeah.
Yeah, I see.
I'm ever so sorry about Faye not being here. I'm also terribly sorry about my yuck technology.
Actually, Jeremy Don't worry at all. And I'm sure, unfortunately, I fear that Faye had, something more important to do. So, and I really hope that she's okay and everything.
Yeah.
Well.
I suspect it's something like, stuck in the London Underground with the train failing or something, because probably trying to go between Imperial College and home.
Yeah, so no problem at all. And I think that you have been exceptional in defending, and in presenting also.
Oh, thank you.
If there are no other questions, we thank our speaker again.
A very great pleasure. Thank you so much for everybody. Goodbye then.